All right, hello everyone. So today we're looking at a couple problems from a top one class. So we have the derivative of two functions. For part A, we have the derivative with respect to x of the function integral from 2 to x cosine t squared minus 1 dt. And for part B, we have the derivative with respect to x of the integral 4 to the square root of 3x minus 1 sine squared 3 to the t fifth plus 8 dt. So the solution, I'm going to be using the fundamental theorem of calculus here. That's our main tool. There's sometimes it's called version number 2, or for the most part I've seen it called version number 2. There's version 1 out there. There's 2 versions. Some people call this one the first version, but I'll just call it FTC, fundamental theorem of calculus. All right, and the fundamental theorem of calculus in so many words says that if you take the derivative of a function defined as an integral that goes from a to x f of t dt, and the derivative with respect to x, the derivative is the function that is the integrand of x, okay? Some people like to say that this theorem provides the justification that every function that is continuous around a value a has an antiderivative, okay? That's another way to interpret this. And some people just simply say that, oh, look, the derivative of an integral is just the function itself, okay? I believe there's more to that than what I just said with that last idea about the derivative of the integral is just a function. I go for more of the first two. Anyways, explanations I give. So we have the derivative of with respect to x of 2 to x cosine t squared minus 1. And essentially, this is set up already for you to use the theorem. The derivative of this would be just cosine of x squared minus 1. It's like you replace the x with where the t is at. So it's just x squared minus 1, and that's how the theorem applies here. Now for our next problem, B, let's move that down here. That's where B was. We have something that looks like what you just worked with, but not exactly, because the top limit is not to x, it's something else. So I can't apply the theorem directly. However, what you can do is you can try to rewrite the function, the integral function, as maybe a composition. So we took a big function, call it big f of x, and that would be the integral from 4 to x, sine squared 3 to the 5th, sine squared of 3 to the t to the 5th plus 8 dt, and g of x equals the square root of 3x minus 4. So think of over here, think of this as the inside function, and this whole thing's like the outside. Then we can look at this as a composition with f being that integral function and g being the square root of 3x minus 4. And just to verify that, if you looked at the composition f of g of x, this would equal what you see here. Okay. And if I were to take the derivative of that composition, I'd have to use the chain rule. And that's what I'm doing right here. I'm just kind of setting the chain rule up. So the derivative of the outside function, big F, would be f prime of g of x times g prime. That's what the chain rule tells us. So in our case, we would have big F of x, and f prime would be sine squared of 3x to the 5th plus 8. That is by the chain rule. F prime of g of x would mean plugging in the square root of 3x minus 4 in for all the instances of x. And finally, g prime of x would be, in terms of the derivatives, not done with the whole problem here, would be something along these lines. So I'll let you double check that. And therefore, our final answer, f prime of g of x times g prime, would equal sine squared 3 times 3x minus 4 to the 5th power plus 8 times 3 over 2 square root of 3x minus 4. Okay? And that would be it. And in general, when you are taking the derivative of a function which has a number as a limit and a function on top here, it's f of t dt, function's continuous around a here, the derivative is equal to f of g of x times g prime. Okay, basically this is just what we just did a minute ago, just applying it and abstracting that idea. All right, thanks for your time.